So these are going to be the answers and problems to your 5 specific heat and calorimetry practice. Let's just go ahead and get started. Number 1 says a block of aluminum weighing 140.0 grams is cooled from 98.4 degrees Celsius to 62.2 degrees Celsius with a release of 4,428 joules of heat. Calculate the specific heat of aluminum. All right, well, with any of these problems, first off, we're working with our specific heat equation, which is just this, Q equals mc delta T. And remember that Q always represents the amount of heat in joules. It's the transfer of energy between differing temperatures. M stands for mass. This can either be in grams or kilograms, depending on your problem. C is the specific heat capacity. Again, it is the amount of energy necessary in order to heat up 1 gram, 1 degree Celsius, and it has the units joules per gram degrees Celsius or joules per kilogram degrees Celsius. And then finally, delta T. This delta represents change. It always is the final minus initial temperatures, and this is measured in degrees Celsius. So let's just plug in our values and try and figure out what we have. My Q is a heat, and you need to always ask yourself, is it an endothermic? Does it gain energy, or is it an exothermic? Does it lose energy and cool down? If it is an endothermic, then your Q value will always be positive. If it is an exothermic reaction, meaning that you're cooling down, then you are losing heat, and it is released, meaning that you have a negative value. Here, that's the case because we have a release of, or you can say that it is cooled down. Either way, you have a negative Q value in this problem. M is going to represent the mass, and here you have 140 grams of our aluminum block. C is our specific heat capacity. This is going to be our unknown. We're trying to figure out how much energy it takes to heat up by 1 degree Celsius. And then finally, change in temperature is the final minus initial, so I'm going to write 62.2 degrees Celsius minus 98.4 degrees Celsius. And I don't want to think about that. Let's just plug it in. 62.2 minus 98.4 equals negative 36.2 degrees Celsius. All right, if we have all of our variables now, let's rearrange this equation, Q equals mc delta T, in order to solve for C. To do that, I'm going to start out by rewriting my equation. And I want C by itself on this side, so I'm going to divide out the mass and change in temperature on both sides. Cancels here, and then I am left with Q over the mass times change in temperature is equal to the specific heat capacity. Perfect. Just plug it in. Negative 44.28 joules divided by our mass, 140.0 grams, multiplied by our change in temperature, negative 36.2 degrees Celsius, close parentheses, and 44.28 divided by. Now, if you are plugging this into your calculator, you do have to be specific by saying that most of the time these bottom values, you have to either multiply them first or you have to plug them into parentheses. If you do that accurately and you solve everything, then you should get a calculator answer of 0.8737, numbers, and I want 3 sig figs off of my 36.2. That is my least accurate, so I am going to count 1, 2, 3. My 7 rounds up, and I have 0.874 joules per gram degree Celsius. It's going to be the answer for problem number 1. Let's move on to 2. 2 goes, in 2 states, a sample of mercury metal is cooled. Well, let's go to cyan, fine. From 52.5 to 25.0 degrees Celsius. In the process, 766 joules of heat is released. What is the mass of mercury that is in the sample? And then it gives the specific heat capacity in kilograms. All right, let's do it. So Q equals mc delta T. I'm just going to start with all of my knowns and unknowns again, knowing that mass is my unknown in this problem. And let's try and solve for the others. Q, again, I am going to have a negative Q value because my heat is released, it is cooled. I am having an exothermic reaction, meaning that I am going to have a negative 766 joules. My C stands for my specific heat capacity, and here I have 138 joules per kilogram degrees Celsius. And then finally, my change in temperature, again, is always the final minus the initial. And my final temperature here is 25.0 degrees Celsius minus 52.5 degrees Celsius to equal a negative 27.5 degrees Celsius change. Okay, now let's just plug it in. Again, I'm trying to solve for mass. So Q equals mc delta T. I want mass by itself, meaning I need to get rid of C and delta T from this side. And if I do it to one side, I got to do it to both. If I rewrite my equation, my heat divided by my specific heat capacity multiplied by my change in temperature is equal to my mass. If you plug it in then, negative 766 joules divided by 138 joules per kilogram degrees Celsius times my change in temperature, negative 27.5 degrees Celsius. Put the bottom in parentheses just to help me out with my calculator. And let's solve for my calculator answer. So negative 66 divided by parentheses 138 times negative 27.5 equals, and I get a calculator answer of 2018,445, numbers. With sig figs, again, I should have 3 sig figs from either my heat. My specific heat capacity is actually given. I don't take sig figs there, but my change in temperature is also a measurement with 3 sig figs, so I need 3 sig figs in this problem. 2, 0, 1, draw my line. My 8 rounds up, so finally I have 0.202, and you can see joules cancels, degrees Celsius. The only thing I'm left with is my unit for mass in this problem, which is kilograms. There is problem number 2. Let's move on to problem number 3. Problem number 3 says a gold ingot with a mass of 192.4 grams is heated from 30 degrees Celsius to an unknown temperature of whatever that unknown temperature is, with the absorption of 927 joules of heat. I give the specific heat capacity is 129 joules per kilogram degrees Celsius, and I am asking for the final temperature of the gold ingot. And finally, I want to make sure, because I gave a hint, that all of my units match on this problem. So let's start it out the same exact way by listing all of my knowns and my unknowns. Mass, C, and change in temperature. Now, I'm going to go and I'm going to actually, before we even get started here, tell you that there's 2 ways in which you could solve this problem. I'm going to solve it by one single equation of I'm going to do a substitution of my temperature final minus temperature initial into this problem, and you're going to see what that looks like. But if you just want to solve for change in temperature being your unknown, then that would be the exact same answer. So let's start out. Heat, I am absorbing heat this time, and I am heating up. So this is an endothermic reaction, meaning that I have a positive 927 joules of heat. My mass then is 192.4 grams, and my specific heat capacity is 129 or just 129 joules per kilogram degrees Celsius. And then finally, my very, very last known is that I know that I have a temperature initial of 30 degrees Celsius. Okay, So if we want to solve this problem, first off, let me show you this substitution that I'm talking about, because I want my temperature final to be my unknown. What I'm going to do is I'm going to write my equation Q equals M times C, and instead of delta T, I'm going to do a substitution, and I'm going to plug it in as TF minus TI. Again, my final temperature is what I'm wanting to get, so I'm going to first get rid of the mass and the specific heat capacity on either side so that they cancel, and I'm going to rewrite it. My heat divided by mass times specific heat capacity is equal to my change in temperature, TF minus TI. Now, I want temperature final by itself, and if you notice, I'm subtracting here. In order to get rid of the subtraction, then I'm just going to add TI to both sides. It's going to cancel here, and if I rewrite it, I'm going to have my heat divided by mass times specific heat capacity plus Ti is going to equal my temperature final. Okay, now before we plug it in, because I'm afraid that I'm not going to have enough space if I try and plug it in and show you why, I have to make sure that all my units match. And what I mean by that is that if you notice, my joules match with joules, that's fine, but my grams here do not match with the kilograms down on the side. I have to convert at some time during this unit. So I'm just going to do that now. I'm going to convert this 192.4 grams into kilograms. And to do that, again, you know we multiply it by a conversion factor. Since our grams are technically over 1, then grams goes on the bottom in order to cancel out, and I am left with kilograms at the top. 1 always follows the prefix, meaning that 1 kilogram is 1,000 grams. Now, all I have to do is you notice that I multiply everything on the top and divide it by everything on the bottom. So 192.4 divided by 1,000 will give me 0.1924 kilograms at the very end. Now, let's just plug it in. So I have 927 joules divided by my mass. I'm going to be sure to use the kilograms one. Kilograms times specific heat capacity. Here, our specific heat capacity is 129 joules per kilogram degrees Celsius, and then I am going to add our temperature initial plus Ti. Oh, but I need to write the actual number for that, don't I? This is the plug-in step. Ugh. So, plus Ti then, here is going to give us plus 30 degrees Celsius. So plus 30.0 degrees Celsius. If I plug everything in, then let's see what we get. I'm going to do 927 divided by 0.1924 times 129. I'm going to get 37.3 plus 30 equals 67.3 degrees Celsius as a final temperature. Here you go, problem number 3. Let's move on to problem number 4, our calorimetry. Okay, in order to accurately perform a calorimetry, remember that there's always a couple of steps. What we are going to be doing is that we're actually going to solve 2 different problems. And what I mean by that is that you are going to try to solve 2 Q equals MC delta T's, but one is for metal and one is for water. So if I have my problem, the Q's actually equal each other because the amount of energy transfer is the exact same. So all you have is that you have a negative mass of metal times the specific heat capacity of metal times change in temperature of metal is equal to the mass of water times the specific heat capacity of water times the change in temperature of water. There are actually 8 different variables that you are working with for a calorimetry equation of, let's just write them all out, and then we're going to go through each specific one so that we know exactly what we are working with and how to accurately solve a calorimetry equation. So temperature final of water and temperature initial of water. Okay, let's start out with a mass of a metal. And thankfully our problem goes and it gives us a mass of metal of 23.1 grams. Then let's just flip to the side and say what's the mass of our water? We know 10.21 grams of water, so 10.21 grams. Now this water has an initial temperature of 26.1 degrees Celsius, okay? And it has a change in temperature, let's just write it down here, of 5.2 degrees Celsius. Meaning, if I think about it, my initial is 26.1. I am going to increase by 5.2 degrees Celsius, meaning that my temperature final of water is 31.3 degrees Celsius. Then, the only other given that they give us is just, again, our specific heat capacity of water. It's 4.186 joules per gram degrees Celsius. So we have over on the side these three specific quantities that are part of a calorimetry equation. The first thing we have to know is that anytime you're performing a calorimetry, your specific heat of the metal is always going to be your unknown. That's the entire point of performing a calorimetry, is trying to determine the identity of that metal. However, your temperatures are going to be a little bit odd. You have to know what a calorimetry is doing in order to accurately solve them. What you do in a calorimetry is you put a metal into boiling water that is undergoing the heat of vaporization on your heating curve, meaning that that temperature stays stable at the temperature of boiling water, 100.0 degrees Celsius. Then that metal is going to cool down, and that energy transfer, that heat, is going to be the exact same as the heat gained over here by your water. If your energy transfer is perfect, then after a specific amount of time, you are going to reach thermal equilibrium, meaning that your two final temperatures are going to be the same. This is how you understand that a calorimetry is done, is whenever the two final temperatures match. Thermal equilibrium means there can be no more energy transfer. So now you have all of your variables. One thing I'm going to do quickly is that I'm going to solve for the change in temperature of just my metal first by doing 31.3 degrees Celsius minus 100.0 degrees Celsius. It is going to be negative because it's exothermic, and that's what, 68.7, I think? 7 degrees Celsius. Now, let's rearrange and plug it in. Let's change colors. Let's go into a nice, I don't know, green, fine. And let's do it. Again, this C of M here, this is my unknown. This is what I'm trying to solve for. So in order to do that accurately, I am going to get rid of the mass of the metal and change in temperature of the metal by dividing it out. I am going to write my rearranged equation as C of M is equal to all of my water values, mass of water, C of water, delta T of water, divided by my negative mass of metal times my change in temperature of my metal. That's going to be my rearranged equation. So now let's plug it in. I'm going to equal mass of water, 10.21 grams, multiplied by my C of water, 4.186 joules per gram degrees Celsius, then multiplied by my change in temperature of water, which we know is 5.2 degrees Celsius, divided by my negative mass of metal, negative 23.1 grams times negative change in temperature of metal, which we solved as negative 68.7 degrees Celsius. I'm going to put this bottom in the parentheses just so that I know to do that in my calculator, and let's plug it in. Of 10.21 times 4.186 times 5.2 divided by negative 23.1 times negative 68.7, close parentheses, 0.14004. So 0.14004, and then numbers, numbers, numbers. If we want to try and decide our accuracy, our sig figs in this problem, our most inaccurate value is actually this 5.2 degrees Celsius. This is our limiting factor here in this problem because this only has 2 sig figs and it is a measurement, meaning that our entire number then will have 2 sig figs. The 0 doesn't do anything, so I write it as 0.14 joules per gram degrees Celsius because all the other units cancel unless you are just left with this. But that is going to be the specific heat of our metal in this calorimetry problem. Let's finally move on to problem number 5. Problem number 5, I went and I had some fun because I gave you a data table, but it's going to be the exact same thing. Again, our problem is negative mass of metal, C of metal, delta T of metal, is equal to mass water, C water, delta T of water. And if we start plugging in all of our knowns and unknowns, we're going to try and see what we can find out. Temperature final, metal, temperature initial of metal. And same for water, mass water, the specific heat capacity of water, temperature final of water, and temperature initial of water. All right, mass of metal, do I have perfect? Mass of metal is 50.33 grams. My C of M is the specific heat capacity of the metal. Remember, this is always your unknown in a specific heat or in a calorimetry problem. Temperature final of metal should be the same as the final temperature of my water, 27.0, because again, we know a calorimetry is done whenever these two are equal. Then my temperature initial of metal is in the boiling water, and yes, it is 100 degrees Celsius. Mass of water, 39.100 grams. C of water is always my given, 4.186 joules per gram degrees Celsius. Temperature final of water is 27.0 degrees Celsius, and temperature initial of water is 22.0. So in my calorimetry, my water had a change of temperature of 5.0 degrees Celsius, and my metal had a change of temperature again, final minus initial, of negative 63. Is that right? No, that's 73, isn't it? Yeah, negative 73 degrees Celsius. So boom, 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 negative 73.0, again, subtracting degrees Celsius. Now, let's plug it in. Again, every single calorimetry is going to use the exact same rearranged equation as well, just because we're always solving for the exact same thing. So there's no guesswork. We know our rearranged equation. I'm going to then plug in my mass of water is 39.100 grams multiplied by specific heat capacity of water, 4.186 joules per gram degrees Celsius, multiplied by my change in temperature of water, 5.0 degrees Celsius, divided by my whole value, negative mass of metal. Mass of metal is 50.33 grams, times my change in temperature of metal, which is negative 73.0 degrees Celsius. Boom. Just plug it into our calculator for a calculator answer. 39.100 times 4.186 times 5.0 divided by negative 50.33 times 73.0, close parentheses, and I get a 0.22 numbers. So let's try and figure out our accuracy, our sig figs. Again, our least accurate value is right here with our 5.0 degrees Celsius from the change in temperature of our water. This is 2 sig figs, meaning our answer needs to be 2 sig figs. We cut it off. This doesn't round at all. And we get 0.22 joules per gram degrees Celsius because everything else cancels in our problem. But that is going to be the answer then to problem number 5. And that is the end to all of your practice problems. Thank you, everyone. I hope you have a great day.